Congratulations on making it to the end of the course. In this last section, I want to briefly mention some neural network topics that I didn't have time to cover in the course, or things that are beyond the scope of this course that you can look forward to learning next. There's really only a handful of things that I skipped or didn't cover, such as different activation functions like Saranich, ReLU, Leaky ReLU, different neural network libraries like TensorFlow and PyTorch, strategies for neural network regression, flavors of neural networks like convolutional neural networks, recurrent neural networks, LSTMs, GANs, GRUs, autoencoders. Then you have applications like object detection, image captioning, text-to-speech, sentiment analysis, text summarization, one-shot learning, reinforcement learning. Oh, and then there's things like batch normalization, savior initialization, root mean square propagation, and adaptive momentum estimation. Okay, maybe there's a lot of stuff I didn't cover, so I'll just pick out a few things to mention and call it a day. First of all, in this course, we used the logistic activation function and we stuck with it. It turns out, when you have a deep neural network filled with logistic activation functions, it can suffer from something called the vanishing gradient problem, where the gradients in the first few layers become so small that they're essentially static, meaning they have an inability to change and improve. The way most people deal with this problem is, instead of using a logistic activation function, they use what's called a rectified linear unit, or ReLU, which looks like this. Now, you might be thinking, hey, that's not differentiable at 0. And you're right, but all we have to do is arbitrarily define the derivative at 0 to be 0 or 1, and then we're good. Another thing you might be thinking is, if we end up in this flat area where the derivative is 0, we'll get stuck there. And again, you'd be right, but in practice, this turns out not to be a big deal because it's unlikely that all of our weights are going to get trapped in these zero gradient situations. However, because of this, some people prefer to use what's called a leaky ReLU, which has a very minor slope in the negative region. Next, how can we use a neural network to solve a regression problem, like predicting the sale price of a house? In this case, the neural network will typically have a single output node without an activation function. By not using an activation function, the output can grow unboundedly small or large. Also, the objective function you'd use would be something like root mean square error or root mean square logarithmic error. Lastly, how do you know how long to train a neural network? In other words, how many gradient descent steps, or epochs, should you make? So far, when we've trained our neural networks, one of the things we monitored was the cross-entropy loss of the training data. In practice, what we really want to do is, first, randomly remove a small portion of the training records and call this a validation dataset. Then, as we train our model on the training dataset, we monitor its performance on the validation dataset. At no point during the training procedure should we let our model use the validation dataset to calculate gradients and improve the weights. And that's the point. The validation dataset is meant to be an unbiased evaluator of our model as it learns. What typically happens if you monitor the loss on the training and validation data is, as your model learns, the loss on the training data tends to get better and better and better. But for the validation data, the loss tends to get better until a point at which it plateaus or sometimes even starts getting worse. This is an indication that your model is overfitting to the training data. And so the optimal number of gradient descent steps you want your model to make is usually the point at which your validation loss stops decreasing. I've actually added validation monitoring to the neural network we implemented in the last section, and you can see validation loss stops improving after about 125 iterations. Now, it happens that retraining the model for 125 iterations on the full training data gets you about 95% accuracy on the test data, which is slightly worse than the 96% accuracy we got when we trained it using 200 iterations. But when we used 200 iterations, we were essentially guessing a number, and we happened to get lucky. In practice, if you do this, you'll typically underfit or overfit to the training data, and your performance on the test data won't be so good. By the way, this technique is not unique to neural networks. It's a common approach used for any model that relies on gradient descent, including things like XGBoost and LightGBM, which are popular implementations of gradient boosting. So with that, I hope you enjoyed this course, and I hope you got a lot out of it. Creating this course actually took me 7 months of writing, coding, recording, animating, and editing, so it was a pretty big undertaking. Any feedback you can give me, good or bad, would be appreciated. And if you enjoyed the course, consider liking, subscribing, and sharing my content. It means a lot. So thanks, and stay tuned for future content.